today we have a talk by Professor Iskander Taimanov from Novosibirsk, and he will speak about formation of singularities of two-dimensional soliton equations. So please, thank you for accepting this invitation.
Okay, thank you for inviting me to give this talk. First time I'm speaking in Rostov. Never been in the city, yes, but now I'm speaking there. I start with the general subject, so because before explaining what are these LAB triples, I have to recall the notion of Lex pair, because LAB triples is just the generalization of this notion onto two-dimensional soliton equations. So the Karapetyants de Vries equation, it was integrated by an inverse scattering method in 1967. And 1 year after that, Peter Lux, in his seminal paper, explained some part of its integrability by introducing so-called Lux pairs. The representation of this equation in the form actually known to Heisenberg in quantum mechanics in 20s, but not in relation with this nonlinear system, which are definitely not from quantum mechanics. The interest in them in the late 60s was initiated by plasma physics. And what is Lex pair? So we have this one-dimensional Schrödinger operator, n minus d2 over dx squared plus u. The u is potential. And we can take another differential operator, ordinary differential operator of third order. Those coefficients depends on u and its derivatives, such that the commutator of L and A results in the derivation of u with respect to time, to temporal variable. So ut is equal just the commutator of L and A, because then we are differentiated L in t. Of course, the derivative of this constant part, this is a second order differentiation with respect to x, is a constant operator. So its derivation with respect to t vanishes, and we are left only with this expression ut, and the commutator gives you the right-hand side to the Karapetyants de Vries equation. It's 6u over x plus u over x. So these evolutions preserve the spectrum of the operator, deforming the eigenfunctions by the rule psi t plus a psi equals 0. The psi is the eigenfunctions on the energy level E. So that was also used after that for finite dimensional systems. In this case, we take matrix operators L and A, and the matrix L, the traces of L and all its powers are preserved by this deformation. It's L is just matrix operator, ordinary operator without differentiation, not differential operator. So this observation was crucial because the traces, the spectrum is preserved. It gives you a lot of first integrals, and also in the early 70s there appears first articles about application of transformation, or the Darboux transformation, to construct a new solution of Karapetyants de Vries equation. What is the Darboux transformation? It's very simple, how it looks like now. For every solution of omega of the equation L omega equals 0, we have a factorization of the operator L in the operator A top and A. The A and A top are formally conjoint operators of the first order. So they had the form A is equal minus d over dx plus v, A top is equal d over dx plus v, and v is logarithmic derivative of omega. The Darboux transformation of, sorry, there has to be L here, not H, consists in just swapping A and T, A top and A. So we're swapping them, and you have the another ordinary differential operator, U tilde, which and this transformation acts on eigenfunctions in a very simple manner. So if psi is eigenfunction of L, then A psi is eigenfunction of new operator L tilde. Eigenfunction which corresponds to the same energy level, to the same eigenvalue. So that's very easy to see from the swapping procedure. So this transformation can be extended to solutions of KdV. So assume that on every moment we're given kind of Darboux transformation of the solution of KdV, and the resulted transformation also gives you a solution of KdV equation. It's not exactly this, so there are some additional terms in this procedure, but the idea is it's just we're extending the Darboux transformation for solutions of the KdV. So in this article in early 70s, it was called Backlund transformation. That was misleading because Backlund transformation has another geometrical background. So what now LAB triples? They were introduced by Monakov in the middle 70s as two-dimensional equations presented in the almost Lax form. LT equals to the commutator of L and A. There, L and A are partial differential operators, which depends on the two temporal variables X and Y, plus BL. The spectrum is not preserved except its zero level. So if L psi equals 0 and the solution of the equation psi t plus A psi equals 0, then it deforms the solutions of this equation. Then it preserves the equation of L psi equals 0. So that's we have eigenfunction on the zero energy level and deform the potential of L, and the function eigenfunction also deforms. So, but I'm speaking now about eigenfunctions in the generalized sense, because I'm not speaking about some eigenfunctions which belongs to some functional space. I'm speaking as a formal analytical solutions of these equations. And there are plenty of them, such solutions. For instance, if the potential of L equals 0, and L is two-dimensional Schrödinger operator with the zero potential, is just the Laplace operator, then psi would be just a harmonic function. Why Monakov introduced these triples? He wanted to generalize the Lax approach to the two-dimensional soliton equation. And it appears if you were starting to construct Lax pairs, which involve the two-dimensional differential operators, partial differential operators with some physical minutes, like Schrödinger operator, Dirac operator, then they cannot get the commutator. And then they cannot get to the scalar operator in the left-hand side just from the commutator term. If they add an additional term BL, we can get the scalar operator UT in the right-hand side. What are these examples? For instance, the Novikov-Veselov equation. It's written here. It's UT equal the third derivative of U with respect to Z plus third derivative with respect to Z bar. There is a Z is the complex variable of the complex plane, or the domain of the complex plane, plus the term is very similar to KdV. It's written here. And also in all these two-dimensional cases, there is a constraint. There is some constraint as V over Z bar equal UZ. The L is two-dimensional Schrödinger operator, but whereas D is the derivative with respect to Z, D bar with respect to Z bar. And they assume that U is real valued. Then this solution is represented as a LAB triple. There is L is a two-dimensional Schrödinger operator. In one-dimensional limit, then U depends only on X, on one variable. It reduces to the Cartesian de Vries equations, because you see we can resolve this constraint because assume that it doesn't depend on y. So in this case, ux equal vx, so we can resolve this constraint as u equal v, substitute this term v into the original equation. All derivatives with respect to z and z bar has to be replaced by derivatives with respect to x, 1 over x over 2, so because it's Cauchy operators, and you will get the Korteweg-de-Vries equation. This equation is not physical, then it was not physical and it was derived. Now it appears that it has some physical applications. But at this moment, it was derived in the framework of two-dimensional Schrödinger operators, which are finite gap on one level of energy. So that was in the framework of a so-called algebra geometric integration of a soliton equation, which was kind of introduced in the middle of 70s in the articles of the Moscow School and the St. Petersburg School, Leningrad School at this moment, and Moscow was Dubrovin, Khrushchev, Novikov. From Leningrad, there were Matveyev, Itz. But in this two-dimensional operator, two-dimensional equations, it was probably one of the first equations. But you see, it was derived in the framework on these equations. But you see that's why it's called Novikov-Veselov, because in this article in 76, Dubrovin, Khrushchev, and Novikov introduced these two-dimensional Schrödinger operators, finite gap on one level of energy, but with additional magnetic terms. So it's not exactly Schrödinger operator, plus, but some additional operator of first order, plus a d bar, which means that we consider the Schrödinger operator with in magnetic field. The spectral data which corresponds to Schrödinger operator were found, or kind of the condition for potentiality of these operators were found by Veselov and Novikov in early '84. And this equation, it appears then in terms of this spectral data, in terms of this algebra geometric spectral data, this Novikov-Veselov equation exactly and immediately generalizes the KdV equation to the two-dimensional situation. It's different from Karamzov-Petuashvili equation because which is also two-dimensional generalization of KdV equation. So the theory was started in '76. These two-dimensional Schrödinger operators, finite gap, and but this equation was derived 8 years later in the joint articles by Novikov and Veselov. Another modified Novikov-Veselov equation. It was introduced in the early 90s by Bogdanov, who was at this moment the PhD student of Monakov. And the idea was the following. So to the Korteweg-de-Vries equation, there corresponds modified Korteweg-de-Vries equation, which is also one-dimensional soliton equation, but for it the L operator is a Dirac operator. So Monakov and Bogdanov were looking, Bogdanov is his PhD student at this moment, were looking for the generalization of a modified Korteweg-de-Vries equation in the same spirit as Novikov-Veselov generalizes KdV. So this is this equation, and in this case, L is a two-dimensional Dirac operator with a real valued potential on the diagonal, U as real valued. So again, in one-dimensional limit, it reduces to a modified Korteweg-de-Vries equation. Now it appears that if we drop this condition that U is real valued, we can represent in this LAB triple form the Davis-Sturzen equation, which was introduced before in the early 70s in articles on hydrodynamics by Davis-Sturzen in the physical articles. It has the following form, which is written on the this page, ut equal y times uzz plus uz bar z bar plus v plus v bar times u, with this constraint v z bar equal to u squared model u squared over z. So it appears, but its triple representation was found later, not by Davis Stewardson, because they were not looking for the soliton stuff. And now I'm coming to the Mutar transformation, which was introduced by differential geometry Mutar. And it is a two-dimensional generalization of Darboux transformation. So if we have the Darboux transformation for constructing new solutions of Karapetyants de Vries equation, we have to look for Mutar transformation for its two-dimensional version to construct new solutions of two-dimensional soliton equations from the given ones. So let's take this L as a two-dimensional Schrödinger operator, d bar plus u, and assume that L omega equals 0, whereas delta is the two-dimensional operator. And now the Mutar transformation is as follows. So we have L operator. Now consider L tilde. It's actually looks almost the same. It's minus delta plus u. And now we have to extract additional term minus 2 Laplace logarithm omega. It's again as how it's in the triple case. It works with the zero energy level of the operator L. So if psi satisfies L psi equals 0, then the function theta, which is defined through these systems, not uniquely, up to additional terms which are multiples 1 over omega. That's clear from the right-hand side. Then the new function theta satisfies the equation L tilde theta equals 0. So in the one-dimensional limit, this Darboux transformation reduces to this Mutar transformation reduces to Darboux transformation. The funny point that the Mutar transformation was found before Darboux, 6 years before Darboux. Mutar considered the operator which in the books of projective differential geometry in the 19th century was called Laplace operator. This it is operator dx dy plus u. So we have hyperbolic operator dx dy. There are x and y as real value temporal variables, and u is potential. So when Mutar, for instance, tried to construct new surfaces of negative curvature from the given surfaces of negative curvature, because you see this is a local transformation, could be defined locally, and the idea was probably the following, because it is discussed on books actually by Finnikov, who on projective differential geometry in Russian, where he explains these results of French school of Laplace transformations, Mutar transformations, and it looks the idea was the following. There was the big problem. So we have now Lobachevsky geometry. We now have, okay, that situation in the 19th century. We now have the surfaces of negative curvature. This Lobachevsky geometry, hyperbolic geometry is realized. But they are constructed in the abstract Riemann way. Just we take the plane and introduce some Riemannian metric. Can we realize this metric as the first fundamental form for some immersion of the surface into R3? That was a big problem at this moment, because all attempts led to appearing of singularities. So we can do that locally, but then the extending, trying to get the complete metric, people arrived to singularities. It was proven at the beginning of the 20th century by David Hilbert that that's impossible. So the hyperbolic plane cannot be immersed into three-dimensional Euclidean space. And at least this idea, this approach to construct such metric was dropped because it was impossible. That the Mutard transformation in this hyperbolic form was saved in the books of differential geometry because it was applied in some other to some other problems of projective differential geometry. And there was a very nice analytical theory of it. But you see, they're working in an analytical stuff. So we have dx, dy, so we can replace x and y by z bar. We do get this theory with now this two-dimensional Schrödinger operator. And we can rewrite the Mutard transformation for this operator. And now I'm coming to the results, to some results. We started with Sergei Tsarev in 2008, where we constructed Novikov-Veselov equation, singular solutions for the Novikov-Veselov equation using classical Mutard transformation. Later, I did that for two other equations, modified Novikov-Veselov and the focus and Davis-Stewardson 2 equations. What are these solutions? The initial data are smooth and fast decaying. Solutions are rational. And at certain critical time, these solutions become singular. So we have kind of blow-ups. You will see exactly what's not, it's very special blow-ups. They're different because for Novikov-Veselov equation, this is classical Mutard transformation extended to the transformation of solutions of Novikov-Veselov from the original Mutard transformation for the Schrödinger operator. For the two other equations, the transformation has a very explicit geometrical meaning. What is interesting? In all these cases, the zero-level energy spectrum degenerates at the critical time, at the terminal time. It appears that the spectrum is not preserved. At this terminal time, it degenerates. One eigenfunction which corresponds to one point of the discrete spectrum blows up. And it looks that that's related with the blow-up solution. So there is some relation. But now I will speak only about examples. That's for Novikov-Veselov. It's very easy. I assume it's not very easy, but the explanation now it looks very easy. I assume they have this function f. For t equals 0, it's positive. Then we started to go to increase t, and until t is less than terminal time, singular time. This is can compute it exactly for this situation 29/12. Then the solution u of the form 2d bar logarithm f satisfy the Novikov-Veselov equations in non-singular. But as soon as t equals 29/12, the solutions we do have two singular points. And then the solutions stay singular for all other times. And what is the eigenfunctions? In this term, this function psi equal x times y over f is the eigenfunction, fast decay, which belongs to the discrete spectrum of this Schrödinger operator. And in this case, the eigenvalue is 0. So you see this eigenvalue is not separated from the continuous spectrum of this operator, this two-dimensional operator. It's on the 0 level. Probably all the machinery of these blow-ups also related to this situation because it's not negative eigenvalues. It's 0 energy level. Now I'm coming to the modified Novikov-Veselov equation. This is, in this case, takes these functions a, b. They again, these are polynomials. And I introduce here the constant c, which comes to this data. And as soon as then t doesn't equal c, this function, also rational, in Z bar U satisfies the modified Novikov equation, and this function psi, which is equal 1 over this modulo a squared plus b squared, and here this is has to be vector function, a bar z minus b bar, a bar plus b bar z bar. So this function is also fast decaying, belongs to L2, and lies on the zero energy level of this operator, this spectrum L. So it belongs to its zero energy discrete spectrum of this operator. But as soon as t equals c, a and b, these functions, these equations gets singularity, becomes singular. And but here there is one interesting point. Assume that's so there has to be some correction. You also see, yeah. There has to be, so there's some misprint. I have to correct it, yeah. Because here a and b vanishes simultaneously. A polynomial vanishes only if c equal t. That's it. So that's, yeah. And now, what is the situation? The integral of u squared dx dy is the first integral of this equation. For the Novikov-Veselov, this integral is u dx dy. So, but that for non-singular time, is integral equals 2 pi for 3 pi, and it drops to 2 pi for singular time, and then it's became again non-singular. Again, 3 pi in solutions becomes non-singular, and the similar with Davis-Stewart's equation. And now I come into the Weierstrass representation of surfaces in R3. And what is this? Assume that we have the operator, Dirac operator, L, two-dimensional Dirac operator, and the operator D, V. This is coadjoint. We swap these terms on the diagonal. And two solutions, d psi equals 0, dv phi equals 0. Then these formulas, where x, k, or z are given by these quantities, define the surface in a form. These formulas were first in this Dirac form introduced by Karapetyants in R3, but in another form that was they were known to Eisenhardt, who used not Dirac operator but two-dimensional Schrödinger operator with singular coefficients and magnetic term. And and then it was generalized by Karapetyants. It's kind of the way of inducing surfaces from these harmonic spinors, from these spinors solutions, d psi equals 0 and dv phi equals 0. What it means? Let's take what's the origin of these representations? Assume that z is a conformal parameter, z equal u plus ev. The u and v is a real parameter. So what means conformality? It means that the metric in the first fundamental form is conformally equivalent to the Euclidean metric. When it is conformally equivalent to Euclidean metric, in this case, then the norm of the vector dx over du equal the norm of the vector dx over dv, and these two vectors also are orthogonal to each other. That's written in this form: the sum over k of dx k over dz squared equals 0. So this is quadric. So we have that's for any dimension. So if they have the surface in n-dimensional Euclidean space and z is a conformal parameter, this means that the derivatives, the squared derivatives of the coordinates with respect to z, the sum of the squared derivatives vanishes. These are complex numbers, that's possible. So now consider this quadric Q just this quadratic Z1 squared plus Zn squared equals 0 in CPN minus 1. So what does it mean? That's you see that's dx and dv. They also define this is two vectors on which the tangent plane is which span the tangent plane. So now we can delete these coordinates u and v, so multiply them by some constant. I can rotate this tangent plane. In terms of the of these vectors dxu, dxv, it means that we can multiply the vector dx over dz by some non-vanishing complex number. So that results. So that's these coordinates the derivative of x over z, the derivatives, this vector defines the tangent plane, but not all of them define the same plane. Two such vectors defined the same plane, if we can get one from another one by multiplying it by some non-constant, non-vanishing complex number, constant. This means only that these are projective coordinates. So they have z1, zn is that projective coordinates. And this mapping from z to this point in the projective space is nothing else but the Gauss map, which maps point z to the tangent plane, oriented tangent plane at this point. So now for n equal 4, what is this quadratic? z1 squared plus z2 squared plus z4 squared. This is nothing else but the product of two complex projective lines, CP1, CP1. This is a diffeomorphism is given by the Segre mapping. This is Z1, Z2, Z3, Z4. This is Segre mapping, which gives you this diffeomorphism. So it's when you will take any A1, A2 and any B1, B2, the 2 points on 2 CP1, to two complex projective lines, and substitute into this formula for Z1, Z2, you will get the point of the quadratic. And back is also correct. So converse is also correct. So for any point to this quadratic, they can construct 2 points. So this is diffeomorphism. So this quadratic Q4 is just, it's not a diffeomorphic, it's holomorphical equivalent to the product of two projective lines. And now in this case, the spin of psi and phi just take this form, phi is equal A1, A2 bar, psi is equal B1, B2 bar. They're reconstructed from from the surface up to gauge transformations. And every surface in R4 has a global Weierstrass representation. So for every surface on trivial topology, we can get this spinors, this phi and psi. But if the topology is non-trivial, they are not functions. They are sections of some spinor bundles all over the surface. This is generalization of the Weierstrass representation of surfaces in R4. Well, in this case, in R3. In this case, Q3, this is a quadratic. This is so this variety G tilde N2 is just the Grassmannian variety. Grassmannian of oriented two plates in n-dimensional Euclidean space. So for 3-dimensional n equal 3, this Grassmannian is a complex projective line. And we again, they have original spinor representation of surfaces in R3. But for higher dimensions than n greater than 4, the quadrics Qn have no such rational parameterizations. So we cannot construct them, we can describe the Gauss map in terms of some rational data and derive such reconstruction formulas. And what are now the Davis-Sturzen deformation of surfaces? So assume they have the this solution of this equation. That's of this equation, psi t equal a psi phi t equal a v phi, such that LAB triples for the Davis-Sturgeon hierarchy, and the potential evolves as a Davis-Sturgeon. The Davis-Sturgeon equation. So we do have the deformation of the Gauss map, and it defines the deformation of surfaces up to translations. So at any moment, the Gauss map defines you the surface up to translation. So we have the deformation of surfaces and additional translation term RT. So they also depend, such deformation also depend on resolving the constraint. Vz bar equal to W squared Z. So now one can define a deformation governed globally by using this constraint such that it preserves the Willmer function. It's the squared norm of the Minkowitz vector. H squared. So this is the Willmer functional. It looks like in terms of this data, it's just the integral of squared norm of u times some constant, which is a multiple of pi. And what is now the Motard transformation of solutions? This is, I call that Motard type transformation. Now let's write down this is a representation of this surface, these formulas. I just would like to recall it. This is, you see, this is x1 over the z. This is term, p2 bar, psi2 bar, plus phi1, psi2, and so on. Now let us identify R4 with the quaternions. The two-dimensional complex matrices which are generated by Pauli matrices and gives you quaternions. So that's this formula S, the surface in terms of quaternions. So this is previous equations are written it's dy over x plus 4. That's so this is where then they substitute the previous formulas. We do have this term, this line, which depends on psi and phi, and this is the surface. They just rewrite the original presentations in terms of 2 times 2 matrices. And now take the Davis-Sturgeon deformation such that for every moment in time it's generated by the Möbius transformation of the surface. So we have the surface S. We do have its Weierstrass spinor representation with some potential U and conformal parameters U on this surface. Now take the Möbius transformation of this surface. Möbius, geometrical Möbius transformation in a form. It's written very simply. We're just inverting this matrix. S goes into S minus 1. So Möbius transformation is conformal transformation of A4. So this is conformal parameter Z again goes to a conformal parameter on the surface S minus 1. For this surface, we do have again the spinor representation. So again, there's some potential U. So now let's take this deformation, Davis-Sturgeon deformation of the surface S, and at every moment in time we shall apply the Möbius transformation, geometrical Möbius transformation to the surface. Reconstruct for it the potential, and what we do have the transformation of solutions of Davis-Sturgeon equations. So this is, first I did that for modified Novikov-Veselov equation, but it was not very interesting probably because this equation is not, has no physical meaning. It's not very interesting, but this is some physical equation. But actually all interesting features of these equations are, or these solutions are similar. So, and for them, it's again for also in this case, we for modified Novikov-Veselov equations, we identify R3 with the imaginary quaternions. Imaginary quaternions. So this is exactly x1, x2, x3, and x4 equals 0. x4 equals 0. There is no constant diagonal term, real value. So these are just imaginary quaternions. So. And again, the surface is realized as surface in imaginary quaternions, and we again we take this Möbius transformation. and it gives you new solutions of modified Novikov-Veselov. And now let us try to apply it to some simple surfaces. The simplest case, just start with minimal surfaces. For minimal surfaces, U potential equals 0. Davis-Sturtson equation gives you trivial solution, stationary, U equals 0. But the eigenfunction is not stationary. If we, what is it? Let's take that's f be a function which is golomorphic in Z. It satisfies this equation df over dt equal I d2f over dz squared. It defines the Davis-Sturtson deformation of the minimal surface Z2 equal fz1. So then the theory of minimal surfaces in F4 was started. There was an idea to find the minimal surfaces, which the simplest example of minimal surfaces in R4. The very first simple example is a special class of surfaces as follows. Take any entire function f of one complex variable, represent C2, R4 as C2 with complex coordinates Z1, Z2, and take the graph of this function, Z2 equals f Z1. So that would be a minimal surface, borrow even superminimal surface in R4. This is the simplest class of superminimal surfaces. Then take this U equal I ZF prime minus F, Z squared plus squared normed, P equal 2I A over Z, where A takes this form, and the U satisfies to the Davis-Sturtson equation. You see that's very similar. That's to what I had written before. Here, the Davis-Sturtson equation. That's also this equation becomes singular. Then the denominator vanishes. Z norm Z squared vanishes when Z equals 0, and then the critical time. Then this denominator vanishes. The same is here. So here, actually, I'm sorry, here everything was correct because A vanishes at the origin, xy. So, okay, I became worried. No, everything is correct here. The same, this is a very simple equation, a very simple solution. And here it's actually one of this form for very simple function f. And then we do have this blow up for the solution of the Davis-Sturtson and how it looks like. I will take more complicated example. Take f in the previous case, it was the f was polynomial on the second order in Z. Now take this polynomial Z4 plus 12i t z squared minus 12t squared plus c. So it definitely satisfies this equation, f over t equal I d2f over dz squared. The solutions take this form. I am substituting the previous formula. It becomes singular exactly then c equal 12t squared. And its singularities are of the form just indeterminacies. So that's then the denominator vanishes. Another part of this fraction also vanishes. But so we have that's zeros on both parts of the fraction, numerator and denominator, and denominator. But you see that's. But we have indeterminacies of this form. U behaves as minus 12t exponent 2I phi. There is phi is the angle in planar coordinates. So the limit of this, it's a solution has the critical point at 0, and it has different limits there. Then they're coming to the origin along different rays. Again, the first integral here is equal 4 pi for t such that u is non-singular, and 3 pi for t then is t singular. Notice that if c is real value, that's possible. If c is imaginary, then there is no singularity. So these singularities are not stable with respect to small variations of the initial data. They're not stable, so probably they're not of very important physical meaning. And now, what happens? Why do appear these singularities? What is the physical meaning of these singularities? And I have to come to the previous formula, this C. So what is it? We have the minimal surface here, minimal surface S, which is immersed into a free. And the surface doesn't go through the origin. So now they're moving this minimal surface. There is some motion. This deformation surface with respect to Davis-Stewardson. It stays non-singular. Okay, it's the potential stays non-singular until this following point. The surface just passes at some moment the origin. This Möbius transformation maps the origin point into infinity. This was actually the Möbius transformation is defined not in Rn, but on Sn. So we have to compactify Rn by infinite point. So as soon as it maps the origin to infinity, we do have the singularity of the potential, singularity of the representation. But then as resumes its evolution and again passes origin at one point and then evolves outside infinity. So again, it becomes a non-singular solution, U. Why this quantization of this Willmore functional by pi? That's also has geometrical meaning. We take the minimal surface and take this Möbius. The minimal surface is just the plane. They take this inversion. Inversion of this plane Möbius surface would be the sphere, singular sphere, but it would be Willmore sphere. So Willmore, some part, some simplest examples of Willmore surfaces in R3 and R4 can be obtained as Möbius inversions of minimal surfaces in R3 and R4. That was known even to Blaschke probably in 100 years ago in differential geometry. But for Willmore spheres, the Willmore functional is quantized by p, so it has values by p times some integer numbers. So all the time we stays in the class of singular Willmore spheres, but then the surface passes through the origin. We do have not only singular Willmore sphere, but they have Willmore sphere with the branch points. The point at which the first fundamental form vanishes. This is branch point. So this is the explanations how this Willmore spheres, this subject of differential geometry, explain this quantization of this Willmore functional. And this picture of the Möbius transformations demonstrates how these singularities do appear for the Davis-Stewardson equation. But I would like to notice that these singularities are not stable, because as soon as I see I just slightly vary it such it becomes its imaginary part would be non-zero, there is no singularity at this solution. So that's for analytical formulas, that's okay. They're not stable with respect to these variations. I would like to say about the Ozawa solution. It's very different. It was found by Ozawa 30 years ago. It is as follows. We start with the following initial data. U, x, y, 0. The u is this, the numerator is this exponent minus ib over 2 y squared minus x squared. It's divided by this term. And let minus a would be positive. This would be singular time. As soon as we start with this initial data, at this singular time, this integral, okay, not the integral, it has to u squared. U squared, that's kind of, it has to remove integral here. It stands to the Dirac distribution centered at the origin, 2 pi delta. So the integral of this left-hand side would be 2 pi, because that would be integral over Dirac distribution. And then at another moments, the solution is again ancillary. It's regained singular. It's regained non-singularity. It's regained. It's becoming non-singular again as soon as we pass this. They pass this moment. In all other moments, it's non-singular. But this 2 pi is the first integral of this solution. It's always 2 pi. But at one moment, all the solution, it gets real blow up, and so all the solution degenerates to the Dirac distribution. And then it's again smooth solution. It's very nice. And there are some numerical experiments that probably is a generic stable, physically stable solution, a singular solution of the focusing Davis-Stewardson 2 equation. But what we did present, we presented completely another kind of singularities. They are different because here you do have jumps of the Willmer function now from 4 pi to 3 pi. Here there is no jumps. It's real first integral. And but okay, they are not stable. So, but this is you see, this is in this case for this two-dimensional soliton equation, which are represented by L-bit triples. The L is the two-dimensional Dirac operator. Therefore, these two equations, we can construct the geometric theory of the Mutar type transformation. They're completely geometrical. They are just they're just induced by Möbius transformations of certain surfaces, deformed surfaces, and they give you some new class of singularities which do appear for this equation. That's probably the most interesting one. Then I will consider it's for Davis-Stewardson, which is a physical equation with important physical meaning. That's I'm sorry that I'm slightly over my time, 4 minutes, but you see, this is a mixture of soliton theory and differential geometry of surfaces, and that I wanted to stress some points, and hence, okay, use the 4 more minutes. And now I'd like to thank you for your attention.
Thank you very much for the very interesting talk. And now it's time for questions. Probably I can ask you. Okay, yes, please.
Well, this is Tunjai Acterson from the United States. So it was an enjoyable talk. Well, I'm not an expert in this area, but I have the following questions. Well, you are doing everything at lambda equals 0. So when the spectral parameter is 0. So normally when you do the inverse scattering transform, well, you consider the entire spectrum, but the spectral parameter is independent of t. So naturally, you get, I guess, rational solutions. So, but at the same time, I wonder whether naming these soliton equations or soliton solutions is justified, because you get the soliton solutions when you consider the entire spectrum, and those soliton solutions correspond to the bound states of the potential in some sense. So that's one remark. And my second remark is that, is it possible to get all these rational solutions that you're obtaining by doing the standard inverse scattering transform, namely without restricting yourself first to lambda equals 0, but by concentrating on the rational solution? In fact, I believe that Ablowitz and some others did many years ago some work on this. Then they obtained the so-called rational solutions. So, in other words, can you, without restricting yourself to lambda equals 0 to begin with, by doing the inverse scattering transform, can you get your solutions by doing the standard inverse scattering transform, and then by restricting those solutions in some sense so that you can get the solutions that you're having? Well, thank you very much.
Yeah, thank you very much for your questions. That helps me to, stress me to recall another point. I do have actually the joint article from my former student Adilkhanov, where we did numerical experiments for Novikov-Vasilov equation. For instance, the negative discrete spectrum is not preserved by equation, because these Elabet triples, they're completely related to the zero level energy spectrum. Discrete spectrum is not preserved, so it evolves. And actually, the inverse scattering transform is well defined in one-dimensional case. The inverse spectrum problem is completely resolved. By here, there we need some tricks, the D-bar problem and so on. And okay, that's quite probably complicated to work. Okay, we have to then resolve from some spectral data, from some Riemann problems, some constructing some potentials for this data. We sometimes have to assume that some additional integral solutions do not, integral equations do not have solutions, and so on. So this is some complications in the in two dimensions, which is different from the one dimension where the inverse scattering method is well defined, well developed for all these equations. And you see, that's another point. That's the discrete spectrum, except the zero discrete spectrum, that's negative discrete spectrum for these operators, is not preserved by these equations. That's the point.
Thank you.
Thank you. More questions, please? May I ask you the following question? Behind this Mutar transformation, there is a factorization of the Schrödinger operator in 2 dimensions, which is precisely like in the one-dimensional case. It looks very similar. So in fact, instead of the Laplacian, one can consider the operator divergence, then some function p of xy gradient. And you obtain is very similar factorization and a very similar Mutar transformation. So my question is that in this case, of course, you arrive at some other equations, not exactly Novikov-Vasilov, but some other equations, because you have another function p. Okay. So if that was done already, and what kind of equations in this case you obtain?
That I don't know. I know that there was some kind of, if we would like the explicit factorization, this factorization method for two-dimensional versions, I remember there was article by Novikov-Vasilov in middle 90s. But this class of transformation doesn't preserve the class of potential operators. Even starts with the potential operator, then doing a factorization and similar to swap, we do get the potential plus additional first order term. So we do have a magnetic field.
I will send you in my book in electronic form, which was published in 2009. It's about the pseudo-analytic function theory. So probably it's all around the factorization of the Schrödinger type equations in 2 and more dimensions.
Yeah, if also just mention exactly this page, yes, just to find it earlier about this factorization, about which you did speak now. Yes, I would be very grateful. Yes. Because I remember there was attempts to do factorization with Schrödinger operator straightforward, but it didn't preserve the potentiality of operator. Yeah.
Okay. So probably some other questions or remarks. Unfortunately, I cannot see if there is some hand. No, yeah. And probably another question, which is more or less related with the questions of Professor Akhtasan. So in this two-dimensional situation, in fact, this triplet Lux type representation, does it allow one to solve just the Cauchy problem, for example, for the Novikov-Veselov equation, for any initial data, or not? Or it's just some relation between different operators, and that's it?
No, that was developed. I didn't work on that, but this stuff was developed, not very intensively, but it was developed, this triple representation.
So one can solve the Cauchy problem, let's say.
For
the Novikov-Veselov.
Yes, we can start this. For Novikov-Veselov, that was studied quite well. Not for modified and Davis-Stewart in this framework, because Davis-Stewart was studied by other means, because it wasn't originally from soliton theory, and a lot of many people had been working on it even before it was kind of immersed into this soliton framework. But for Novikov-Veselov, that was developed. There are plenty of articles for Cauchy problem.
Okay.
I think there was some remember articles by Perry, Siltonen, and some other co-authors where they discussed some conjectures. What has to be the initial data? So they have to separate initial data from the Cauchy problem such that they apply the regularity of the solution for all time. So our examples with Tsarev were used as the test examples. So that's probably the conjecture. This looks like initial data is this done. Probably that's the only singular solutions. Yes, only the data which lead to singular solutions.
Okay, thank you. So if there are no other questions, thank you very much again for your very interesting talk.
Thank you very much. It was my pleasure.
Thank you very much.
The discussion was very interesting. I'm waiting for your book.
Thank you, and see you in 2 weeks.